Alright, so this time we will be talking about fluid as continuum. In our previous discussion, we discussed about the characteristic of the fluid. As we know that we have two different types of fluids. We have the liquid, and we also have the gas, or gas, matter in gaseous form. And we already understand that fluid occupies all available space in a given volume without leaving any gap. And also, if we're going to look at the distance between the molecules from each other microscopically, we can see that there is an average huge distance between the different molecules, okay, in microscopic level. So this means that fluid continuously spread in any available space. Okay. So if we're going to look at fluid and we're going to study the characteristic or the behavior of the fluid, it is important to determine what particular level of volume, okay, of a particular fluid to determine its behavior or its characteristic. Alright. And also, the fundamental characteristics of fluid can be analyzed by looking into its mass in a given unit of volume under a particular standard condition. Okay, if we will say standard condition, that is, for example, at 25 degrees Celsius at 1 atmospheric pressure. Right? Let's proceed. Okay. In this slide, so what we have here are how the readings of density can vary from from different point of the fluid. Okay, so looking at the illustration in this graph, in the three-dimensional graph here, the red here is our fluid, and if we're going to look at the density here at point 1, it varies as we go along to point 2. Okay, so we might perhaps have this particular reading that if we will start from x sub 1 and we move towards x sub 2, this is how the graph might look like. Okay, so why we have this particular readings? Why is it that we could have an erratic or non-regular reading of the level of density as we move from point 1 to point 2? Alright, the reason for that is because the concentration of mass, or the number of matter, or shall we say the number of molecules in a particular snapshot, okay, of the event, shall we say x sub 1, is not the same as we move to the different points of the fluid. Okay, we might see a lot of molecules at this particular portion, and then if we move to x sub 2, for example, we just have we can read relatively low density, and as we move to the next point, we could read higher level of density. Okay, why is that so? Because we understood that molecules of the fluids are always in motion, especially when they are exposed to higher temperature, or there will be a variability of temperature reading. Okay, so if we're going to look at to the microscopic level of the fluid, we could see a density reading like this as shown in the graph, right? So it might shoot up and then suddenly goes down, and then it goes back again, and and then we could have a low reading of density until such time that uh, we can have a reading that is almost constant. The density is almost constant, not changing. Okay, and then the variation of reading of density is again evident. All right. So yeah. So if we're going to look going back, if we're going to look at in a microscopic level, this is how we have our or read our density, the level of density. Okay, it varies. And if you're going to enlarge the amount of volume to that particular point of the fluid, we could have this particular reading, okay, shaded in the gray lines, I mean shaded in a gray portion. And then if we're going to enlarge further, again, the reading of density will vary. So at this point, we could see that there is a particular portion of or level of volume that we could take the behavior of the fluid, right? So this is called the limiting volume. Okay. So in this slide, we have here, okay, the limiting volume, or the dV prime, which is approximately 10 to the negative 9 cubic millimeter. Okay, that's the volume, 10 to the negative 9 cubic millimeter. The behavior of the fluid at a standard condition at this particular level of volume is somewhat like less in less chaos. Okay, so we could have a reading of density that's almost constant, almost, not perfectly, okay, because it also varies if we're going to look at it. And yeah, and if we enlarge this volume, we are actually approaching to this microscopic variation. Okay, so if we go smaller than 10 to the negative 9 cubic millimeter, we're approaching the microscopic fluctuation. Okay, so yeah, in microscopic fluctuation, so the density is erratic. All right. So if we're going to look at microscopically, like illustrated here in figure A, we could see that the density at this level is high. All right. Then if we're going to enlarge the volume from that particular level, we could assume that the reading of density drops because of the voids that we could see in between the molecules. And if we're going to look at C, the number of voids versus the number of particles in a particular portion of the fluid is somehow constant, although this particular the particular molecules, or the number of molecules in this particular amount of volume is changing, but the reading of density here is not erratic as what we've seen in the microscopic level. Right. So because of this, we take fluid as a continuous distribution of mass rather than individual molecules. So that is why in fluid as a continuum, we ignore its particulate nature, of the material. Now, so looking back at the volume, okay, so if our initial volume is expressed as, if our initial density is expressed in dm sub 1 over dv sub 1, if we're going to change that, if we're going to enlarge that, so that could be the density will be dm sub 2 over dv sub 2. So as we enlarge the volume, so that can be denoted with this equation, that is density is equal to dm sub n over dv sub n, okay, which is m is the mass and the v is the volume. Okay, so dv prime is actually the limiting volume, as what I've said a while ago. So that is the smallest region of interest where all fluid properties are point functions. And limiting volume is important in fluid mechanics because it helps us to make assumptions about the fluid behavior. So again, the limiting volume, the dv prime, is about 10 to negative 9 per 10 to negative 9 cubic millimeter. That is true to all types of fluid, liquids, or for gases at atmospheric pressure also. Okay, so if we will say atmospheric pressure, that is 1 atmosphere or 101,325 pascals, right? So for air, if we have 10 to negative 9 cubic millimeter, that's approximately 3 times 10 to the power of 7 molecules. Alright? And we also have this what we call control volume. Control volume is an arbitrary volume in which the mass of the fluid remains constant. Alright? So, control volume is used to study the flow of fluids through a given region. Right? So if we're going to describe more about the property or the characteristic of the fluid, we can use the following measurement or quantities. Those are these are the basics. So the following are density, the specific gravity. Specific gravity is also known as relative density. Okay, and we also have the specific weight, the temperature, the pressure, the specific volume, the surface tension, compressibility, viscosity, capillarity, and cavitation. Okay, if we will say surface tension, that is actually the boundary between the two different kinds of fluids. For example, if we're going to look at a glass of water, you can see at the top portion of that there's a film. Okay, so that's what we call the surface tension. So we can see the boundary there of the fluid and the gaseous form of the matter.